Hi everyone, I'm Curran. Today I'm going to talk about integrating and visualizing heterogeneous data cubes. So the whole idea is that there's value in visualizing many data sets together at the same time. And this is difficult to realize because there's a lot of heterogeneity in the formats and protocols and the levels of detail used and the various identifiers used in publishing these data sets. I had this idea that there is a universal model that all of these data sets can fit into based on this idea of a data cube. And I'll talk about data cubes more. So my contribution is this framework where you can model these data sets, integrate them together, and visualize them as one unified structure. So the related work is in the area of data representation, data integration, and data visualization. In data representation, there's a long history of representing data as tables. Like Excel is widely used to publish data and to use data. Relational databases are a very mature platform for representing data. And today, with the scale of the web, NoSQL systems have sort of become more popular. The semantic web is a vision for this integrated web of data, but that seems not to have really taken off as much as it could have. And data cubes, the concept of a data cube is very old. It came out of the data warehouse field with OLAP systems, online analytical processing systems. There is an RDF vocabulary now for representing data cubes as RDF. And several people have introduced mathematical formalisms where they define the structure of data cubes in terms of math. So in terms of data integration, this is also kind of an old field. There's this authoritative textbook, Principles of Data Integration. And the main problem is schema mapping, where you have different schemas, like different tables with different attributes and values. And you need to match up the attributes between tables when they refer to the same thing. Like population in one table might be the same as pop in another table. And they may use different keys to represent the identifiers of each thing in the table. So say there are two country tables, one uses a country name and another uses a country ID. The schema mapping deals with matching these keys together. And also, there could be different scales used. So, say the one table has population in billions and another has population in millions. These scales need to be reconciled together. And there's a long history of work in this, global as view, local as view, constraint-based systems. This is the general idea of data integration, where there are different data sources. They have, local schemas, and there's a global schema that represents sort of a union or a combination of these local schemas. And the client queries this public interface, and then the system deals with integrating the data, querying the sources, and giving back a result in the global schema. So global as view is a schema mapping technique where there are views defined on the sources in the global schema. And local as view is the other way around, where the data sources are defined in terms of the global schema. And more modern approaches just use constraints and say these are equivalent, like this is the mapping, and then some system figures out how to compute the queries. And RDF, the semantic web, also claims to be like the greatest data integration platform, and a lot of work has been done with RDF data integration. Data visualization is a very old, mature field. Semiology of graphics is one of the seminal works where this guy Jacques Bertin from France figured out what kind of data best maps to what kind of visual representations. So like numeric data, which you can scale, maps well to, for example, size. And categorical data maps well to, for example, color. Jock McKinley extended Bertin's work, and this links to a PDF of his paper. I just want to pull it up and show you. the mapping between data and visual elements that he's defined. It's kind of an extension of Bertin's work. Later on in the talk, I'll refer to visualization theory, this idea of visualization theory. And this is what I'm referring to. There are basically three different kinds of data fields: qualitative, ordinal, and nominal. Quantitative. Quantitative fields are numerical. They have a scale. They can be compared to one another in terms of ratios. Ordinal data are distinct entities that have an ordering, like small, medium, large. Nominal data are distinct entities that don't have natural ordering, like, for example, the countries of the world. And these are the various visual channels which are best, according to him, for representing these different kinds of data. So position, the XY position on the plane, is the most powerful one. Length, angle, slope, and area can represent quantitative fields. Color, hue, texture, connection, containment can represent ordinal fields. And it's fairly similar for nominal fields. So this is Jock McKinley's theory. The Polaris system is a visualization system that was the predecessor to the commercial package Tableau. And they have dealt with visualizing data cubes also. The Grammar of Graphics by Leland Wilkinson is another seminal work that defines like an algebra for defining visualizations in terms of tables and statistical data. Visual OLAP comes out of the doctoral dissertation of Svetlana Mansman in Germany. She sort of defined visual OLAP as a new frontier of data visualization, visualizing data cubes. Brushing and linking means an interaction in one visualization has some kind of impact in another visualization or many other visualizations. And with data cubes, you can use one visualization to define slices in another. And the Weave project is also related. That's the project by the IVPR lab using Flash, visualizing data tables and doing many other things. It's a wonderful project. I want to talk also about web graphics technologies because this is what I'm building on. Canvas is an HTML5 technology for 2D immediate mode graphics where the graphics code issues commands to a stateful graphics API. SVG, Scalable Vector Graphics, is a 2D retained mode graphics API for the web, meaning retained mode means that the way you use it is you define a listing of objects and then the system, the SVG rendering system, takes care of rendering them and updating them as they change. WebGL is like a port of OpenGL for the web, so with this you can do 3D graphics and hardware accelerated 2D graphics. D3.js is like the visualization library that's taking off in industry. You can define all these different kinds of visualizations with D3, and D3 uses SVG most of the time, but it can also be used with other technologies. And Leaflet.js is a great JavaScript library for making interactive maps that are based on image tiles in the background. And there have been several visualization libraries built on top of Leaflet that let you do choropleth maps or glyphs on top of maps. So these are kind of the foundational web technologies for graphics and visualization. Now, I want to talk about the concept of a data cube and really explain it because it's a foundation of what I'm doing. So this figure is from a paper about the Polaris system. Multi-scale visualization using data cubes. So they explain the notion of, they have a great explanation of data cubes in the paper, by the way. But this is one example data cube that they have. It's sales data about different products like coffee, espresso, tea, herbal tea, across different locations, like regions of the US, I suppose, east, west, central, and south, over time. So this is for 1 year. There are 4 quarters in time. So for each combination of location, product, and time, there are numeric values for like the sales the success of the sales, like how much profit was made on that particular product in that particular location at that particular time. So that's the basic structure of a data cube. And it's called a cube, but it could be n-dimensional. It doesn't have to be 3-dimensional. You could have 2-dimensional, 3-dimensional, 4-dimensional, and it could go up and up. With data cubes, there's a concept of projecting the data cube. So here's an example where you take maybe the sum across all locations, and you sort of forget about the location, and now you have a 2-dimensional data cube that only varies across time and product. And you can project it further into, you can collapse the product dimension, only look at time. So this would give you maybe a timeline showing how your profit is changing per quarter. And you could project it all into one number, which is the sum of the profit for all products over all time, over all locations. So this is one example of a data cube. Now, I'm proposing that most data sets that are interesting can be modeled as data cubes. But not all data can be modeled as data cubes. And here are some of the properties that will allow a data set to be modeled as a data cube. It's a data table where some of the attributes are aggregated numeric properties. And these are called measures in the data cube world. For example, population, employment, life expectancy, or average income. These would be examples of measures. And some of the other attributes need to refer to distinct categories. And in the data cube terminology, these are dimensions. So for example, countries, years, genders, industries, ethnicities, religions, things like that. But data that represents graphs or networks it doesn't really fit into the data cube model. And data where each row represents an individual event or a transaction, that also doesn't really fit into the data cube model. Like the data cube only represents aggregated data. And relational databases where one thing has many of another thing, and that thing might have many of another thing, that doesn't really fit. So normally the Earth is partitioned in like countries and sub-parts of countries that are political boundaries. But you could also partition the Earth like this, with a sphere cube, a quadrilateralized sphere cube. So this is where you have a cube projected onto a sphere, and each face of the cube is a quadtree, where it's decomposed into quadrants, and those quadrants have subquadrants and so on. So this is one way of partitioning the Earth to accommodate sort of like infinite resolution data. Like if you have points on the Earth and you want to aggregate those points, or maybe satellite data that has different properties of the Earth that you want to categorize. So that's like basically infinite resolution. I mean, it's very high resolution, and you can aggregate it along a structure like this to transform it into a data cube so it can be used with visualization tools that are based on data cubes. The vision is to provide the equivalent of a telescope where people can use this tool to look into the world. It gives people a view into the world, what's happening in the world. What's the quality of life for people all over the world? Or maybe like how have people spread across the Earth? Or things like that. You should be able to use this tool to ask questions about Earth and about the history of humankind through this lens of data. And I'm focusing on public data because that's the kind of data that I can use. But it could be applied to any kind of data. Proprietary data would also work with the system. But I'm just not really focusing on it because I can't access that kind of data. So the way things are now is like this. There are many data sets available. But each data set is available in maybe a couple different formats, but there's not really like one unified format where all the data sets are available in that format. And then you have many different visualization tools. And by visualization tools, I mean like some particular software package you can download and use. Each visualization tool can only consume a limited number of formats, and there are visualization techniques implemented in these various visualization tools. And what I mean by visualization technique is like sort of a more abstract kind of visualization, like an approach to visualizing data. Like a scatter plot is a visualization technique that's available within many different visualization tools. Or a bar chart, or like parallel coordinates, or a table, or heat map. So right now, if you want to, if you say, I want to visualize the Bureau of Labor Statistics employment data with a bar chart, that's linking a data set to a visualization technique. And then when you try to do that, you face the reality of like, okay, I need to pick a particular visualization tool, and then I need to make sure that that tool works with the particular format that data set is available in. And you need to do all that manual work. So ideally, it would be easy to pick a data set, pick a visualization technique, and say, make it work, make that visualization happen. The solution I propose here is this idea of the universal data cube, a data model where you can model all the data sets in terms of this structure. And then these various visualization techniques can be implemented on top of this data structure. And then in the resulting system, you would be able to pick a data set and pick a visualization technique, and the system would be able to figure out the mapping for you. So the expected contributions of this are novel data structures and algorithms for data cube integration, visualization of the integrated data cube structure, and the ability to assemble multiple linked views from this data structure and the visualization technique. So multiple linked views, I mean like a dashboard where you have one thing on the bottom and one thing on the top, and interactions on the thing on the bottom will influence the slice of the data shown on the thing on the top. And in addition to this, what will come out of this work is a visualization taxonomy, like a taxonomy of visualization techniques based on the data cube structure that they're capable of representing, and also an index of public data sets and what their data cube structure is. So I have preliminary results for each of these, and these will be expanded throughout the course of the work. So here's a preliminary data model of what is this integrated data cube structure? What does it look like? This is the simplest possible structure I could come up with. So you have data sources, for example, like the United Nations or the U.S. Bureau of Labor Statistics or the U.S. Census. Within each of those data sources, there are many data sets. And this is crow's foot notation. It's a data modeling notation that says when there are these crow's feet, it means this thing has many of this other thing. And when there's a bar going across, it means that this thing must be a part of one of these other things. So it's just a has-many relationship. It's like a parent-child relationship. So for each data source can contain many data sets. And a data set has many observations. So the observations are the cells in the data cube that contain the actual data. There are dimensions and measures in data cubes. So these correspond to classes in this data model. A dimension could be like space or time or industry or gender, things like that. And a level is a level of a dimensional hierarchy. So for example, in the space dimension, there could be levels of like countries, U.S. states, U.S. counties, metro regions of cities, or in time, levels would be like years, months, weeks, days, quarters. Those are what levels are. And members are particular things within each level. So within the year level, for example, a member might be like 1999. Or within the level of countries, there would be one member for each country of the world. So that's what members are. And measures are those aggregated numeric properties. An observation has many members. So, for example, like one observation might express the fact that the population of Massachusetts in 1990 was some number. That observation would have two members, 1990 in Massachusetts, and the measure would be population, and the number would be there. So that's the idea of the data model. Yeah?
Could you describe the name description, please?
Yeah, so this is sort of subject to flux, but my idea was each of these things would have a name where you could refer to that, and that string would be surfaced in the visualizations as part of the UI, and a description would be just a free text description of what it is. So like maybe like an abstract of the Wikipedia article for it, something like that. These are just so that they can be used in the user interface. Yeah?
You didn't just explain what a crow feed without the bar is.
Oh, without the bar? So that means like one observation has many members, but not every member belongs to an observation. They call it optionality in the literature. It means like it's a cardinality constraint. So one observation must have at least one, it belongs to at least one member, but the member doesn't
Doesn't have to have an observation.
doesn't belong to an observation. Right. So it means an observation it just refers to many members. It doesn't belong to. It's not like inside of the member. Yeah.
Does the observation refer to many members, or is it just a number of? Is it just an observation that is referenced by multiple members?
So the observation references the members. The members don't reference the observations. Yeah, these things, dimension level and member and measure, these stand independently of the observations, and the observations just point to these. Each observation has references to the members, measures, and the data set. Yeah.
I don't quite understand how you can have, on the middle one, on observation, there's crow's feet on both sides.
Yeah, it means that for a given member, there may be many observations that refer to it. That's what this one means. And then this other one means that for a given observation, it can refer to many members.
Data types, fixed code versus state name.
No, so the member is, so he gave the example of FIPS code versus state name. So the member represents the state, like that entity. And there's going to be another part of the model that I don't show here that has the different kinds of identifiers that could be used. Yeah. Question?
So I guess what you're saying is that if I bring to you a new data set or a new whatever that might be that you don't know about right now, and I bring it to you, then this will categorize that data set.
Right. That data set will be linked in. Right. So the import process, to take a given data set and import it, all of its field would be matched up to entities in this model. Yeah.
Is that mapping automatic or semi-automatic?
So it'll be manual. It's beyond the scope of my project to automate that. Yeah, I'm just coming up with a model and a means for people will have to write some code to import each data set for now. But I just don't want to take on too much, But that would be a direction of future work, definitely, to automate the import process.
I couldn't understand in your writing why is not a measure, a dimension.
Why is a measure not a dimension?
Yes, because say I have a data set. I usually call a dimension is describing some information that's in there about a phenomenon or a source, and measure is one type of it. If I remove measure from counting it as a dimension, then when I mention the dimensionality of my data, I will have to remove population, I'll have to remove, ranks, all sorts of qualities that you measure from the set of dimensions. Or did I miss something? I'm trying to actually fit my data into these models, so I I would be a potential user in the end.
Uh-huh.
You know?
Yeah, so you make a really good point that one way to do this would be to model each measure as a dimension. That's very true.
Sure.
And in some data cube models, I've seen them do that, where a dimension, one of the dimensions is the set of measures.
Maybe that's not something that has to be answered right now. Just some food for thought.
Yeah, that's great. That's definitely something I'll consider. And this is just a first stab at it, and this will be evolving. So maybe that's something I should consider, is make one dimension the measure dimension. Yeah, thanks for that input.
Yeah.
Another part of the expected contributions is a taxonomy of visualization techniques based on the data cube structure that they're capable of representing. So this is a first pass at it. Bar charts and pie charts represent data cubes that are one dimension and one measure. Scatter plots represent one dimension and two measures. So that one dimension defines what each point is, and the two measures are the x and y axes. And this is just a first stab. Again, it's not perfect, and it's just like out of my head. But hopefully by the end of the actual dissertation project, the generation of this table would be automated and would contain more detail about what the mappings are. Like each measure, one measure is the x, one measure is y. So I don't think I'll go through all these, but it just gives you a sense that the visualization techniques can be categorized in terms of the data cube structure that they're capable of representing. And another part of the contribution would be an index of public data sets in terms of their coverage over dimensions and measures. And again, at the end, this table, the generation of this table should be automated and would contain more detail.
Does that mean that you're just going to take the data set and feed it into whatever algorithm and have the output as a data cube data set?
So the question was, does that mean you'll feed in a data set to some algorithm and then the output would be a data cube? The answer is yes. The idea is that over time, many data sets can be imported into the system, and the import process will annotate them with what dimensions they cover and which measures they cover. And so there would be a little bit of metadata about the actual data set that will allow something to iterate over all the data sets and compute this table. And also that it'll be used in the visualization tools too. So this gives you a sense that the most common dimensions are space and time. The Bureau of Labor Statistics employment data set covers U.S. states, U.S. counties, and it covers years, quarters, and months, different levels of detail and time. And there are also other dimensions like industry, the hierarchy of industry categories, and the ownership category, like if it's the private sector or government sector. I've made a number of prototypes for this project. Not all of them will end up in the final dissertation, but I just wanted to show you a few things that I've done so far. So as part of a class project a while back, I worked with another student to import the Bureau of Labor Statistics data set into Tableau and visualize it. So this one shows pay, average annual pay. So this is an example of using a bar chart to visualize one projection of the data cube. So from this bar chart, you can see that people who are managers, like CEOs, make a lot more than everybody else. And people in food services make the least, around $15K a year. So another bar chart of that data set is the average annual pay by state. So the y-axis is the same here, and the x-axis is different states. So you can see that people in Washington, D.C. make a huge amount of money more than all the other states. And I just want to point out that this is a data cube. I just want to give you context that it's still a data cube. And a lot of these dimensions are hierarchical. So this is about what we could do with Tableau. Tableau couldn't handle the hierarchies. We couldn't say to Tableau, oh, this thing is hierarchical. Could you please zoom in for me to all the counties? You know, it just wasn't capable of it. So that's one example of using Tableau to visualize a data set that can be modeled as a data cube. Another data set that I've imported and visualized is this United Nations population data. It's hierarchical again. It has world, Africa, Eastern Africa, and then all the countries. And it has this for the entire world from 1950 until 2010. And this is all I've done so far with that data set, is made this timeline of world population from 1950 until 2010.
So this is just the number of people.
Right. It's the number of people on Earth. And so I made this visualization with D3, and it's basically using a CSV file. But this is a first pass at the implementation, and the idea is that this visualization would be one of the many that are generalized to work with this data cube structure. So another data set that I've been working with is the Centers for Disease Control mortality data set. It's causes of death by year and by state, by race, by sex, by age. It's a complicated data cube. This is one data set I plan to import into the system. This is what the raw data looks like in terms of the tree. It's an indented list where the indentation might be spaces, but it might be some weird unknown character. So I wrote some script that parses this into a tree structure, and this is a tree visualization of all the causes of death in the US that they have data on. So you can see a lot of it is just different categories at the top level, but some of them have deep subtrees, and these are cancer, all the different kinds of cancer here, and cardiovascular diseases, like heart attack and stroke and hypertension. So this is one visualization, a node link diagram of the tree that just shows the hierarchy but doesn't show any measure values. And here's another visualization of that data set. It's a stacked area chart where this is time, and each area is one cause of death. So you can see that cardiovascular diseases, that's the top cause of death. And second to that is cancer, and then respiratory diseases and so on. And then I made an example of multiple linked views, where the hierarchy on the side shows the tree, on the left side shows the tree, and on the right it shows the stacked area chart for that level of the hierarchy. So here, the black ones have subtrees. The black nodes have subtrees. So if I click on cancer, that will sort of drill down into the cancer section. So I can see these are all the different kinds of cancers. Trachea, lung cancer is the top cancer, it turns out. And you can drill down further into leukemia, these other types of cancer within this category. So this is an example of multiple linked views where one view lets you navigate in the hierarchy and another view shows a data cube projection based on the other view. Do you have a question?
Yeah, the question was, the assumption is basically that the data is just presented in data cubes, so it allows you to sort of project really quick.
So the question is, the assumption is that the data is a data cube, so it lets you project quickly. Well, the data cube already contains all the projections.
So it's different views of the data.
Right. So this visualization contains different views of the data cube, like different projections of it. Yeah, different slices of it. And the idea is that this would be one example of a visualization dashboard where you should be able to just swap out the data and have the visualization work with another kind of data. So this could be, for example, the world and all the countries of the world, and this could be population. So you can see how the population of countries shifts over time. So that's one idea with this.
Guru,
Yeah.
were all of these prototypes done with D3?
Well, the first ones were using Tableau, those bar charts, but the rest of them are using D3.
Did you convert the data to a data cube, or was it already formatted like that?
Originally, they were CSV files, and a lot of these prototypes are actually hard-coded to the data set right now. There's not yet that generalized data cube form yet.
Right.
So I just used standard D3 techniques, formatting it into a a tree structure that D3 expects. That's how this tree thing works. And the other one is basically a CSV file. And this visualization is filtering the entries based on what's shown in the tree. Yeah.
Right. So basically, you're just visualizing the data sets.
Yeah.
Cool.
Yeah.
Okay. Thank you.
This is something I worked on for a class project, and this one's not actually using D3. This one's using HTML5 Canvas. So I did this in a class project for computational geometry with Karen Daniels. And the idea is when you visualize countries or any kind of region on Earth, the data that you get that defines the boundary for the country is way more detailed than what you can actually download to the browser. So I made this little system that partitions the points of the polygon based on this quad tree representation. So as I zoom in, it gives you more and more detail. And this line on the bottom is showing the number of vertices present on the screen. So you can see it's always below 155. The max is 155 so far. And you're zooming in and seeing more and more detail. So I don't know if this is going to end up in the final dissertation project, but it might. You know, it would be very powerful to have this in the map visualization to simplify the polygons as you zoom in. Another prototype is this dashboard editing tool. So I did an internship at a company called Rapid7 over the summer, and I was building an interactive visualization dashboard for their security-related data. And they let me open source this part of it, where it's a dashboard configuration tool, where this is JSON data that configures the dashboard, and this is the dashboard itself. So you can see here that each of these are editable. And so here, like for example, I can change the size. It's normally really fast, but it's the Skype video connection is, I think, making things slow. So you can see if I update this here, this number down on the bottom changes also. And if I click on this number, I can change it, and it will change what's there. And I can also pick the color. So this is an example. This is a very simple example where it's just like not really visualizations. It's just these X's. And here's an example with text. And here's an example with a map, where if I zoom in here, you can see the coordinates change over here. But the idea is this framework can be used to assemble visualization dashboards with multiple linked views later on. So once I get the generalized visualization techniques implemented on top of the data cube data structure, they can be used in conjunction with this framework to create dashboards that have interactions between the views.
Well, but what about the interaction that happens in terms of listening to events and menus and that kind of stuff?
So what about the interaction with events and menus and so on?
In other words, I might have an idea of, gee, put a menu item up here, and when I press this button that doesn't exist yet, then some other graph comes up. Something so.
Yeah. I mean, so the question is about adding user interface elements like menus. Like, how would you do that?
Then you got to add that framework to that.
Maybe. I mean, my idea now is that is kind of beyond the scope of the project. I don't plan to have a whole user interface framework where you can add and remove visualizations. My idea is just to provide this JSON editor. But that's definitely in the future work category, is designing a user interface for constructing these visualization dashboards and wiring them up to define which view defines what aspect of the other views. Yeah, but it's beyond the scope. And here's a screenshot of what I did at Rapid7, the visualization dashboard. So this shows user logins. Pie charts on the map show success versus failed logins. And this bar chart shows the different ways that people log in. And this shows the timeline of when people log in. And you can filter in any direction. So if you zoom in on the map, these bars change and the timeline changes. And if you select a box on the timeline, it filters at all the other views, and the same with the bars. So unfortunately, it's proprietary stuff, so I can only show a screenshot. But this is the kind of thing I want to be able to implement with data cubes. these multiple linked views where each view filters the others in some way. My plan of action here is to introduce a generic data representation framework for integrating and querying data cubes, survey visualization techniques and data sets in terms of their data cube structure and the various formats and protocols used by the data sets, and the interaction techniques afforded by each visualization. I will develop a proof of concept system using HTML5, importing several data sets and implementing several of these visualization techniques, create dashboards with multiple linked views. And also what will come out of this is sort of a general conceptual framework that maps the data cube structure to visualization theory. So like Jock McKinley's theory of how different attributes should best be visualized, that can be corresponded with the data cube concepts. And I hope to defend the final dissertation in August, if all goes well. So future work includes handling big data, like really big data sets, where the data cube extends like to terabytes. That would involve probably caching and tiling, but that's kind of beyond the scope of the project. The dashboard construction user interface, there's a lot of work that could be done there, but I'm also saying that's beyond the scope of what I'm doing. But I had one idea that it could be a data flow network where you could define like the output of one visualization, of selection, for example, on one visualization, could be linked up to the input of the slice for another visualization. So maybe you could take inspiration from these data flow programming environments that exist. End user programming is another direction where, so my idea is this is, I'll create a seed of this project where there's just a few data sets and a few visualizations, but others throughout the world could add over time their own visualizations and data sets and extend it into kind of like a Wikipedia for interactive visualizations. So that's the idea. So part of the future work would be to build tools that let people program and like save new visualization techniques and import their own data sets into the system.
So in other words, a scripting language. Think of it as a scripting language for i.e. end user programming.
The question is, like a scripting language for end user programming? Well, I was envisioning more like a little IDE in the browser that comes prepackaged with all these visualization APIs. So the idea is it would be a high-level API that people could come and use and just program their own visualization in JavaScript with this API, and then save it, and then it would be available for other people to use. That's the idea.
Who was your target audience for this?
Oh, great question. Who's the target audience? Oh, I forgot to put a slide in on that. The target audience. So the three main application areas I see for this are in education, journalism, and public policy. So in education, the idea is that all this public data could be integrated and then visualized by people who are teaching students about the world. So people who, like history teachers or something like that, or people teaching about just the condition of people on Earth, sociology or something like that, economics. There's, Geography, yeah, teaching geography. Like each country has a profile that you could visualize in some way. So education, and then in journalism, the application of this in journalism is huge because tons of stories in the news, they often refer to some statistics like, oh, this is the second largest country in terms of blah, blah, blah. But then you could really back it up with these visualizations. If you put the visualization right in the article, and it could be interactive to let the users interact with the visualization inside the article. And public policy. So a lot of policies are made on the basis of like people saying this and that without really backing it up. I mean, I don't know, but this is what I've heard. But the idea is that with these visualizations of public data, people can make fact-based decisions. You know, decisions of policy based on the actual facts of how things are.
So, based on that audience, there are not programmers. I know it's future work, but you might want to consider something like a visual programming language, incorporate Blockly or something,
Oh, yeah.
To be able to generate that JavaScript. User doesn't ever need to see it, and that's a lot easier for non-programmers to deal with.
So the comment was you could maybe incorporate something from visual programming languages like Blockly. And like, yeah, that's a great idea. That's a great idea. So hopefully this API that will end up being created, maybe you could connect a dimension like with a wire on the screen to the input of like the x-axis on a visualization or something like that. So, but yeah, that's definitely a direction worth exploring. But for the sake of graduating, I'm saying it's future work. Other ideas are collaboration is another direction, like having people be able to interact in real time with one another. So somebody navigating the views and everything, and that navigation could update for like 10 other people at the same time. Like maybe you could have a virtual meeting with this.
Your taxonomy, it can be used both to translate your data, to talk about your data, and about the visualization. So what you're doing is expressing things as data cubes, and then data cubes as visualizations, so that if people can, or you can translate various data files to the concept of data cubes, you have a way of outputting to visualizations. Is that what I understand?
Yes, that's right. The idea is that as soon as a data set is imported into this structure, then all of these visualizations, or at least the ones that match the data cube structure of that particular data set, will be available for use.
Right. So let's say I'm a user of your final system, and I have a data set. Will I have some sort of support to translate that into your structure?
Well, I think practically speaking, I'm going to import the data sets by writing scripts. And if someone wants to import the data into the system, they can look at my scripts as examples, and then they'll have to write their own code to import the data.
So you say you have to write code to import the data. Why don't we just use D3?
So the question is, you say you have to write code to import the data. Why not just use D3? Well, even if you just use D3, you have to write D3 code that is specific to the data set. So in the world of D3 right now, how it is like when somebody wants to go and use D3, the process is, okay, I'm going to have my data file, it's a CSV, I'm going to get it into the JavaScript world somehow, and then I'm going to look at all the D3 examples, each of which is hard-coded to some other data set, and I'm going to copy and paste that D3 code and then change the dataset specific example to be now specific to my dataset. And I'm proposing introducing a whole new layer of abstraction in there so that you can make a D3 visualization that is implemented in a general way with the DataCube API. And then the idea is once you import the data into this framework, you'll have access all of a sudden to all these visualizations that have been coded in that way.
So why would someone use your API as opposed to Google Fusion Tables?
So why would somebody use this as opposed to Google Fusion Tables? Well, Google Fusion Tables, what does that do exactly? I think it
allows you to merge tables from different sources into one view, which you can then query as a Google SQL.
Yeah, so Google Fusion Tables does that data integration thing where you can merge tables. Well, that's a good question. Well, the idea is that I think if you do it that way, each time you want to refresh or add a new data source, you need to do a lot of manual work, like import the data set into Google Fusion Tables, export it, and then change your visualization code to match up to the new table, right?
And in your system, you wouldn't have to do that?
In my system, you would just have to import the data set, and then it would automatically be able to combine all the existing data sets and then visualize them. So you wouldn't have to change the visualization code for each new data set imported. That's the idea. Yeah, question?
I think you could add some value in terms of helping the user determine which, by a set of a priori rules, helping the user determine which visualizations are most appropriate for viewing his data set, or data set. He's gonna have several data sets, I'm sure, but helping him decide what's the best visualization to apply.
Yeah, so the comment is you could add value by suggesting certain visualizations for a given data set. And that's very true. Like, so if I'm coming up with this taxonomy itself will, given a data set where you know the data cube structure, you can match that data cube structure to these visualizations and instantly get a set of visualizations that apply to that data set. So yeah, that's definitely a relevant direction. Yeah, for sure. Did you have another question over there?
Yeah, basically what you're doing is you're defining a new global schema, correct?
The question is, you're basically defining a new global schema. Yes, but it's not a global schema of any particular thing. The global schema is a general data cube representation frame.
Right. Instead of taking a small set of data sets with a small set of local schemas, you're trying to represent a very broad range, potentially a complete range of possible local schemas.
The question is, you're trying to, instead of representing a global schema for a few target data sets, you're coming up with a global schema that should be able to cover almost any data set. And yeah, that's true. That's true. The global schema in my setup here is like this. It's a schema that defines data cubes in general. So as soon as, yeah, you should be able to map hundreds of different data sets to the schema, regardless of the particular members or measures that they contain, because those members and measures are themselves part of this schema. So it's in a sense a meta model where you can import all the data sets into this. Yeah. So
You got maybe one or two.
So I have a few more slides. I want to acknowledge a few people. The committee, of course, Professor Lefkowitz, my advisor, Jesse Hines, and Professor Mingham. Thank you very much for supporting me in this. George, I want to acknowledge George Grinstein. He's helped me a lot in my life and got me started in the field of visualization. I was in his lab for a number of years. I'd like to acknowledge these people from University of Konstanz, Daniel Keim, Peter Bach, and Florian Mansmann. I spent 2 summers in Germany, and that's where kind of the seed of this project got started, and they helped me out a lot in thinking about this idea. I want to thank Sam Adams at Rapid7 for allowing me to open source that dashboard configuration thing. And of course, my friends and family. You know, my parents have been very supportive of my education. I couldn't have done it without them. And my great friends. And that's it. Yeah, you can clap. It's okay.